Welcome to EPG's video demonstration of oscillation analysis using PGDA. In this video, we will showcase a new automation feature of spectral analysis that expedites the oscillation analysis by allowing users to identify participating PMU locations using a search. The search automatically scans through the list of PMU locations and gathers those that are oscillating in the same modal frequency, either together or against the user-selected reference signal. First, let's spend some time on what oscillations look like and how we characterize them. Oscillations are first characterized by modal frequency, which is the inverse of one cycle time in seconds. For example, a power signal that swings back and forth one full cycle every 4 seconds is considered to oscillate at 0.25 Hz. One that swings one cycle per second is considered to oscillate at 1 Hz. One that fluctuates at 4 cycles per second is considered to oscillate at 4 Hz. The modal frequency is used to help identify the root cause of the oscillation. For example, oscillations in the range of 0.01 to 0.15 Hz are typically attributed to a malfunction in the speed governor of a generator. Oscillations between 0.15 and 1 Hz are commonly known as inter-area oscillations, where one or more units are oscillating against each other. Oscillations ranging from 1 to 5 Hz are usually caused by a local controller, and oscillations greater than 5 Hz are usually attributed to HVDC and fax controllers. The second characteristic of oscillation is energy. This is measured in terms of peak to peak, which is the distance between a peak and a successive valley. The two examples shown in the slide are 60 megawatt oscillations peak to peak and a 20 megawatt oscillation peak to peak. Note that the energy changes over time and hence can be used to quantify the oscillation performance. For this demonstration, we have prepared an example data file of a fictitious power grid. In this example, the PMUs are deployed in 4 quadrants of the grid: north, south, east, and west. The PMUs are named apple in the north, pumpkin in the east, watermelon in the west, and orange in the south, each followed by a number. Here is the offline analytics platform for PMU analysis, Phasor Grid Dynamics Analyzer, or PGDA. It is now loaded with the example data file. An operator from the control room called and said that an oscillation occurred in the northern part of the system. He requested that we investigate the behavior of the oscillation by performing post-event analysis. We will set our objective to determine the root cause of the oscillation, what PMUs are participating, and the location with the highest energy. We will start by first filtering the list of signals to voltage magnitude. Next, we will choose a signal in the north and perform a spectral analysis. This signal becomes a reference signal for finding other participating locations. PGDA shows several spikes in the power spectral density plot, each of which indicates the oscillation or modal frequency present in that signal. By zooming in on the first highest pinnacle, we can see that there is a 0.75 Hz oscillatory mode. Recall that 0.75 Hz belongs to the inter-area oscillation band. Next, we want to find what other PMUs are participating in this oscillation, so we will perform a search. The search function enables us to automatically find signals that A. have a high coherency, meaning they too see the same oscillation, B. have a modal frequency within our specified range, and C. meet our cross-spectral density requirements, which we will discuss further in a bit. Notice that the frequency range in the search window is populated from the zoomed-in x-axis plot set by the user. Since we know the frequency we are looking for, we will further tighten these values to 0.7 and 0.8 in order to ensure the results are focused on our 0.75 Hz oscillation. The cross-spectral density, or CSD, enables us to search for those signals that are at the extreme ends of the oscillation. Here we are looking for signals whose CSD is either smaller than 10 degrees, meaning they are on the same side of the oscillation as the reference signal, or are oscillating together, and signals that are greater than 170 degrees, meaning they are on the opposite side of the reference signal or oscillating against it. When the search completes its process, PGDA plots only those locations that match the search criteria on coherency, frequency range, and cross-spectral density. By using the crosshairs, we see the values of each signal displayed on the right side panel. Here, each signal is listed with 3 values. The power spectral density has 2 values separated by a comma. The first is the decibel value that is on the plot, and the second is the peak-to-peak energy. Next is the coherency value of the signal, followed by the cross-spectral density for the selected 0.75 Hz oscillatory mode. The first thing to notice is that the result set only includes PMUs from the north and south. Second, the PMUs in the north all have a CSD of less than 10 degrees, and the PMUs in the south have CSD greater than 170 degrees, which means that the mode is oscillating from north to south. There are too many locations in the south, so we will redo the search with a tighter CSD of 179 degrees to narrow down the results to the extreme ends on the south side. The results of our final search allow us to conclude that the highest energy is from the north and the extreme end is in the south for this event. The highest energy is at North Apple 596 with the peak-to-peak energy of 0.27 kV. The locations in the south oscillating with the north are Orange's 505, 549, 737, and 740. The spectral analysis provides us with the power spectral density, coherency, and cross-spectral density. We found the highest pinnacle at 0.75 Hz using power spectral density. Hence, the root cause is an inter-area oscillation. We used a search function to find locations that have the same mode by setting the coherency at 70% or greater. We set the search for the cross-spectral density criteria to find locations that are oscillating together or against the reference signal by looking for those whose CSD are smaller than 10 degrees or larger than 179 degrees. And by using the crosshair results, we were able to determine the location with the highest energy and locations that are oscillating against the north. This concludes the video demonstration of oscillation analysis using PGDA. We hope you found this helpful and informative. Please feel free to contact us at Electric Power Group for more information on this and other power system related topics. Thank you.